Hello, everyone, and welcome to today's webinar, Why Use Transit Time Flow Monitoring for Hydro Applications. My name is Eric Lott. I'm the Marketing Manager here at ADS and ACCUSONIC, and I'll be serving as your host today. Today's presenter is Guy Miller. Guy is our Engineering Manager at ACCUSONIC, and he has over 26 years of experience in acoustic flow measurement. He holds a Bachelor of Science in Civil and Environmental Engineering from Worcester Polytechnic Institute and is a registered professional engineer. So thank you, Guy, for your ongoing contribution to our industry, certainly all you do for ADS and ACCUSONIC, and especially today for all the time and effort that you put into preparing the information for this webinar. So without any further introduction, Guy, I'm going to turn it over to you.
Thank you, Eric. And thank you everyone for joining this webinar today. We're going to talk about ultrasonic flow meters in the hydroelectric industry. Just a brief order of how things are going to play out is we have discussing the products and operating principle of our technology, what goes into the measurement uncertainty, and specific hydro applications where our flow meters fit. On the product side, we have two main transducers, transducer types that we utilize. On this screen, we are showing our feed-through style transducers. So these transducers penetrate through the pipe wall, and we have basically three main models that are used for this hydro industry. The 7600 and the 7660, those are a transducer and feed-through set with a integrated ball valve, so the pipe can be isolated when transducers are removed under pressure. Those are good to about 1500 psi, so that would be kind of our high head application transducers. Our 7601 and 7641 transducer feed-through assemblies are probably our most popular in the hydroelectric industry. Again, they can be removed under pressure. They are good to about 450 psi, and we have a high pressure version of the 7641 feed through that's good to 900 psi. And again, fully removable under pressure. The ball valve gets moved to a tool as opposed to on the feed through assembly. And then finally, our third option for the hydroelectric industry would be 7601s and 7625s. The 7605s are constructed of 316 stainless steel and are good to a much higher pressure, 2000 psi, whereas the 7625 is made from a Delrin material, and those are good to 500 psi. The main difference here on the 7605 and the 7625 is the transducer element is removable under pressure, but the window is fixed. So the window cannot be cleaned without dewatering the pipe. So that's why we typically lean towards the 7600s and the 7601s. For applications that do not have external access to the exterior of the pipe, we have internally mounted transducers. So for those penstocks that are encased in concrete, we have three main models that we use here. The 7618, which we call our eyeball transducer, those are designed and well suited for like low head intakes, where you have convergent pipe sections and non-uniform pipes and channels. Our model 7634 transducers is another popular one. It has a dual element. So there's basically two transducers or two transducer faces built into each transducer. And it just has a little bit of redundancy. So if a customer can't dewater a penstock very frequently, they'll typically go with this style transducer. So each transducer body has two cables coming off of it. Those are good to 450 psi, and the utilization of a primary element and a backup element helps. If a transducer weakens over time, you can switch the elements at the electronics console. And then probably our most popular internal mount transducer is the Model 7658 transducer. It's all PVC construction. Um, these transducers are good to about 250 psi. Can be, again, encased concrete. It can be in a open channel application. It's pretty versatile transducer. It's also very low profile, so it doesn't create too much disturbance in the flow stream. One thing that I didn't mention before is our internal mount transducers operate at a frequency of 500 kilohertz, and our feed-through style transducers are 1 megahertz. Getting into the electronics console itself, our Model 8510 Plus, we basically sell two options. It's a 4-path or a 10-path unit. Each electronics console comes with the ability to measure up to 5 different pipes. And the number of pipes you can have kind of depends on the number of paths you have assigned to each pipe. For the 4-path flow meter, we have 4 analog inputs and outputs that come standard. For the 10-path flow meter, we have 8 analog inputs and outputs that come standard with the flow meter. We typically provide 6 relays as well, and each flow meter comes standard with Modbus, which can operate RS-232, 485, or TCP/IP. It is a LCD touchscreen display. Comes with an internal data logging function. It's user selectable as far as whether it's on or off, the frequency, whether it's every 5 minutes, every minute, every second even. Nice feature about this as well as if there's a temporary test being done, the user can put in a USB flash drive into the flow meter and temporarily log to that flash drive as well. Diving a little more into the outputs, again, we provide the unit with 4 to 20 milliamp outputs. They are isolated, so we power the 24 volt DC loop. 600 ohms is a typical load. The nice thing about these 4 to 20 outputs is they can be digitally adjusted, meaning you can digitally trim them to 4.00 and 20.00 milliamps to avoid any type of offsets in your outputs. For Modbus, it is RTU. The most popular is probably RS-232. It is a DB9 no modem terminal. The baud rate is user selectable between 9600, 19.2, and 38.4. Parity is also selectable. And everything here that's shown in bold applies to whether it's RS-232, 485, or TCP/IP. So every one of those protocols, we have read-write registers. It is in 32-bit floating point format. The 3x range is designed for read-only, but we do mirror that in the 4x range for those customers whose Modbus masters can only communicate in the 4x range. The beginning portion of that 4x range is the read and write, so that would be your parameters, and the read-only registers would be your variables, path gains, flow rate, volume, etc. And if you are a customer who has a 16-bit Modbus master device, you basically just have to swap the byte order for Little Endian mode and to convert it into 32-bit floating point. Specific to Modbus 485, it is a 2-wire connection, and the device ID is selectable on the touchscreen display, anything from 1 to 255. And for TCP/IP, the really only difference there is that the IP address, the subnet, and gateway have to be programmed into the flow meter to communicate with the Modbus master in the TCP/IP realm. Switching gears and going into the operating principle, this is transit time ultrasonic flow measurement. So the methodology here is, again, transit time. We do have, in the hydroelectric industry, we're typically dealing with full pipes. So we have 2 main integration techniques that we use for full pipe applications, and it's the what we call the Chebyshev integration. That's for all circular penstocks, and we use the Gaussian integration for anything that's non-circular, whether it's a rectangular conduit, a square conduit, horseshoe tunnel, anything full pipe. And then on the left here, we have typical partially full applications. This isn't typical for for the hydro market, but we do this for other industries such as irrigation and et cetera. As well as potentially doing power canals. So the trapezoidal or rectangular section would be kind of for a power canal situation. So the way the technology typically works is we have an upstream transducer and a downstream transducer. We send a pulse that goes with flow and against flow, and the signal travels faster with the flow, goes slower against the flow. That delta T, that time difference, is directly proportional to velocity. Getting into the measurement uncertainty slightly, these are our typical uncertainties that we expect for various configurations. The detail on the left here shows what the integration uncertainty looks like. So kind of along the lines of any type of measurement, the more times you measure something, the more accurate you're going to be. So you can see on the left-hand side here, if you are only measuring a single point and trying to resolve the average velocity from that, you have a much greater uncertainty than down at the bottom here where you have 4 chordal elevations. You can see that uncertainty band gets much tighter because we're actually measuring those at 4 discrete points. So for a typical 4-path or a 4x4 system, we're typically looking at plus or minus 0.5%. And we can also do 2-path or 2x2 systems, which are in the 1.5% of actual flow rate range. And a lot of times we're asked, what's the difference between a cross path and a single plane system? The cross paths are used when you have any type of non-axial flow components, whether it's induced by a upstream bend or a pump that's inducing swirl. In those cases, we use a cross path configuration, which basically corrects for any type of bias in one direction. For ASME PTC 18, we typically need 10 upstream diameters and 3 downstream diameters in order to utilize a single plane system. The sequence of operation of the flow meter is such that we have a series of transducers and cables that connect up to the flow meter, and we actually transmit at a fairly high voltage. It's about 800 volts DC, but it's only a microsecond wide, so it's a very short, quick pulse. So we basically send the transmit pulse through the transducer and into the cable. The ceramic inside that transducer excites and sends a sound wave out. So that comes through the mating transducer, which would be the downstream transducer in this case, and that goes through the cable and back up to the flow meter. We actually record that time and then we reverse it. So instead of going from the upstream to downstream transducer, now we are transmitting from the downstream to upstream transducer. We repeat that over and over again until all the paths are fired, and then all the travel times are recorded. And then we compute the velocities here over on the bottom right-hand side, where we have basically 3 variables to calculate velocity. We have the path length, that's the transducer face to transducer face measurement. We have the path angle, and that is that path angle there with respect to the center line of the pipe, typically 45 or 65 degrees. And the travel times that we've measured. Those all compute into velocities. We do this over and over again until ultimately on the bottom left side, we come up with our flow rate calculation. And all it is the wetted area times the weighted average of the individual velocities. The uncertainty analysis, once we get into it, it is quantifiable. They do recommend doing it for contractual turbine testing and stuff like that for ASME PTC 18. The quantifiable values here are path lengths, path angles, travel times, transducer protrusions, the wetted area, the integration uncertainty, and the random error. Those all get summed together utilizing the root sum squares method, and we're typically in the 0.5%, plus or minus 0.5% range. And you can see that the important thing is when we're looking at all these individual values, the two main contributors, or the primary first order contributors, are the wetted area, and that's just because the radius or diameter is squared in the area calculation, so the actual uncertainty gets doubled. And then the integration uncertainty, and that's basically how well we are resolving those individual velocities into an average velocity. Getting into the hydropower applications, again, this technology is ASME PTC 18 and IEC 6041 compliant. It can be utilized for Francis pumps, pump turbines, Francis turbines, Pelton units, Kaplan units, power canals, and for specific applications in those turbines, you can have penstock flow measurement. You can do over velocity penstock protection, where you have the flow meter installed up near the intake of the unit, and you can trip an alarm that can close a gate if you get over a certain flow rate. You can use this flow measurement for turbine efficiency and performance testing. So the important thing there to note is that this technology is an absolute flow measurement technology. It's not a relative flow measurement technology. So it can be used to determine actual turbine efficiency and can be used for contractual performance testing. The other thing that the flow measurement can be used for is to create an as-needed turbine maintenance program, as opposed to just doing something annually every year. For those Kaplan units that maybe was just upgraded or overhauled, you can redo your cam curves, verify that your current cam curves are the optimum setting for the wicket gate and blade angles. And then the nice thing about this technology too is you can use it for plant optimization. So if you have a plant that has 4 units, you can actually compare unit 1 to unit 4, unit 2 to unit 3. You can determine which one's the most efficient unit, which one's the least efficient unit. So you can determine which one's my first one on, last one off, or last one on, first one off. This picture shows the difference between a feed-through style transducer that's installed at a 45-degree path angle and one that's installed at a 65-degree path angle. The one on the right is a very large diameter penstock. I believe it's about 6.5 meters in diameter. So we utilize a 65-degree plane to shorten up the axial distance and reduce the path length value, which will increase the signal strength of the transducers. The other nice thing about the 65 degrees, we typically try to utilize 45 degrees just because the cosine of the path angle is much less sensitive at 45 degrees than it is at 65 degrees. But if you have a tight constraint from the ball valve to the scroll case, that's very short axially, that 65-degree path angle will actually reduce and maybe potentially fit in that location. This is an image of, it was an 18-foot diameter penstock. This is an internally mounted system. It has the 7658 internal mount transducers. So they get mounted on the penstock wall. These were stud welded in place. It's a little hard to tell from the details of where the transducers are, but you can see the conduit runs coming from the upstream side to the downstream side. They get collected in a conduit manifold and then come out of the pipe through our cable penetrators. Again, this isn't technology that's strictly applied to circular penstocks. Anything that's non-circular, we can measure. It's as long as we can identify the wetted area, we can measure it. The image on the left is showing our 7634, the redundant transducers mounted directly to the pipe wall. And then again, just the detail on the right showing that we can do horseshoe type tunnels. And then low head Kaplan intakes. These are typically the hardest thing to measure. They're usually two to three bay unit intakes. They're 20 feet wide by 40 feet wide typically. For this specific application that we have shown here, it was for Kootenai Canal, and it was done a good number of years ago now, but it was part of the ASME PTC 18 low head initiative. And we utilized, instead of a 4x4 8-path system, we installed an 8-path system. So it was basically 9 chordal elevations, cross paths. We were in the transitional section from the rectangular section to the penstock. We basically, the ASME PTC 18 actually tested a number of different technologies, and everything was referenced to a master meter that was installed about 20 to 25 diameters downstream in perfect hydraulic conditions. And the nice thing about this is and it was blind testing, so we didn't know where we were stacking up with the master flow meter. But after the test, we found out that we were within 0.1% over the entire test program. And we also able to back calculate what the difference would be between the 18 path system and the 8-path flow. And that was obviously very, very negligible, 0.001%. So typically in this type of low head Kaplan intakes, we can get better than a percent. All right, Eric, it looks like we've reached the question and answer section. I think we have some time for some questions.
Great. Thanks again, Guy, for all this great insight on transit time monitoring. I always learn something from these webinars, and certainly have learned a lot, especially about the applications for transit time flow monitoring. Did not know a lot about those, and I appreciate the insight. So thank you. As Guy mentioned, we did receive some questions during registration. Received some questions by email. We're just going to answer 2 or 3 of those today during the webinar. And certainly if you have submitted a question, we'll make sure and respond to those just as promptly as we can after the webinar. So this first question, Guy, is what are the straight run requirements for cross path systems?
Good question. As I mentioned before, for going from a single plane system to a cross plane system, we tip an ASME PTC 18 does say basically 10 diameters upstream and 3 diameters downstream. For ASME PTC 18 specific applications, they note that you can have 5 diameters. You can utilize cross path down to 5 diameters upstream and 3 diameters downstream. In our experience, if it's not a contractual performance test, we can get down to basically 2 diameters, 1 diameter downstream of a disturbance and still measure very accurately with a cross-plane system. We did a application up in the Pacific Northwest where we had an 18-path system, 1 diameter downstream of an elbow. It was somewhat gentle. It was probably about a 45-degree elbow, but we were able to correlate the 18 path versus the 8 path, and we were basically within 0.1%. So you can get very, very good values or very good accuracy with a cross path system with upstream disturbances.
Great, great. This next question here is, do your flow meters require annual or periodic calibration?
No, they do not. So during the transducer installation, we take a number of what we call as-built measurements. That's the face-to-face value of the path length. We measure that path angle with respect to the center line of the pipe, and we measure the wetted area. So it's been called a number of things: dry calibrated, site certified. But basically those dimensions don't change over time. So there's no drift associated with penstock expansion or contraction. Um, and again, that flow measurement doesn't drift over time, and it doesn't need to be calibrated. So as long as the system is fully operational, all the paths are working, there's no need to annually calibrate it.
Super. Thanks, Guy. I'll tell you what, let's make that our last question for today. Of course, we'd love to continue to receive your questions and your comments. So if you have a question or if you would like additional information on what Guy has spoken about today, you can email me, elot@idexcorp.com. My email address will be on the screen in just a second. Guy, if you go to the next slide, again, we did record this webinar, and I'm going to send you proactively a link to the archive recording that you can share out. Also, I wanted to personally thank you for all the feedback from all the past webinars, especially those webinars that we've conducted since the first of the year. This absolutely helps us. It guides us to provide our presenters with the type of content that you want to see us present, and that's what we want to do. So we have other webinars scheduled for the second half of the year. But again, the content will be based on the feedback that you provide from today's webinars and webinars from ADS and ACCUSONIC in the past. Okay, that is it for today. Again, we thank you very much for joining us, and this will conclude today's webinar.